Hey, hello. This is episode 2 of Ladybug Tools 1.8 question answer or troubleshooting, and we just motor. In the last video, the last question really caught my attention. It's a challenge and I cannot stop thinking about it. It's about if we could use Octopus to iterate the forms of buildings. Well, yes, you can, but it's in context of a script I did a while ago which talks about outdoor comfort and wind analysis combined. Now, a few things. Octopus is a multi-objective evolutionary solver or optimization tool, similar to Galapagos, which we have already installed with Grasshopper. I will use Galapagos if we go there any further. And then the script I did in the past was an very simple outdoor comfort script combined with the wind analysis through the butterfly CFD tool. Just for you to understand the context. In a nutshell, it's like if I, for example, move the building, would that improve the outdoor comfort on the site? And like, if you think about positioning a building on a site, how would it influence the site, either positive or negative? The wind is a third component which actually allows you to dive a bit deeper into that and see where could be a problem with wind tunnel effect, or sometimes this is actually good because it gives you a breeze and it cools you down. Now the problem is the original script is very specific. It's a script which is a point in time script which only looks at 1 hour of the year in terms of outdoor comfort. And because wind analysis the butterfly CFD wouldn't work over a longer period of time. Eddy3D might be working. We could look at that at some point. If you don't know Eddy3D, it's a similar tool as Butterfly. It's more up to date actually. I haven't yet looked at the latest version. I should. But the problems are the same. Butterfly CFD need to create a case for each iteration. That's a huge problem. First of all, how to make that automatic, that it creates a case. There's a purge function which doesn't work, or at least it doesn't work when I set it up. It has a lot of small bugs. It's endlessly in a beta version, so that makes it really difficult to work with. It's still useful, but only for very specific tasks. It also, with each iteration, it writes a huge amount of data on your computer. It's also an optimization tool. That means it makes the calculation finer and finer and finer. So where do you actually start a new case is the question. How fine do you want to have the detail? So there's loads of problems that comes with this. And when I face a problem like that, then what I try to think is, how can we break it down in smaller tasks? And that gives you probably even more information at the end. I would ditch the wind component first. I would go with a generic wind understanding and first reiterate or iterate through the buildings with the outdoor comfort only, and then try to add and make sense with the wind. Now let's try to do that. I just make a very simple plane, the same what I did last time. This is really just to give a very simple script. I always think it's easier to work with very simple scripts first and then apply them to more and more complex problems. So it's a very simple site. Okay, let's very quickly build outdoor comfort script. So we need Ladybug, of course. I go from the source, I call it the source, or the tool itself, to whatever I need in front. You will see it right away what I mean by that. So we have the Ladybug UTCI comfort. That's what we want to calculate. This is our tool. And this time, I don't forget, we want to put the bifocals here so you can see the name of the tool as well. All right, so we need here certain things. We need the air temperature, the MRT, the mean radiant temperature, yes. Relative humidity, wind velocity, UTCI parameters, and run button. Let's start with this. So we need a weather data. This is our tool to download the weather data, and with this one we can search for the weather data. Boolean toggle. I'm gonna go a bit quicker because I cover this a lot. Let's look for something in, I don't know, Spain, France, or I don't know. Well, Switzerland has a lot. Let's take this. Put your copy. You can also download it. I explained this in other videos on how that works. If you download or copy. Copy is actually the same. It just downloads the thing. I put here what the copied URL. And now I have a weather data. And it is import weather data. So the dry pulp temperature is same as the air temperature. Then we have relative humidity. That goes in here. And actually we have a wind understanding. So we have wind velocity. It doesn't give us the wind direction. This is one of the problems. But let's see how we could solve that as well. Or at least to a certain degree. Now, alright, so that's okay. But we don't know what is the mean radiant temperature. So for that we need to look here. Where's the mean radiant temperature? Where do we get that? Already forgot again. Oh yeah, here. Ladybug Auto Solar mean radiant temperature. So now for the Ladybug Auto Solar MRT we need the location. And we have here. Surface temperature we could use here. We could use the dry pulp temperature, or let's see what it says. A single number or an hourly data collection with the temperature of surface around the person in degrees Celsius. This includes the ground and any other surfaces blocking the view to the sky. Typically, auto dry pulp temperature is used when such surface temperature is unknown. So yeah, we don't have the surface temperature, so let's use the dry pulp temperature. But keep that in mind that if you know a certain temperature outside, then you could actually use something else here. Direct normal radiation, this is here. The diffuse horizontal radiation, the horizontal infrared, and then we have fractional body exposure, sky exposure, ground reference, solar body parameters. So as you can see, there's more to that, of course. It also needs a run button, by the way. Okay, let's get this here. Oh, so we have this. We set this to true, and then it gives us an output here. And this is the output we can place in here. Now this also needs a run button. And we calculated the UTCI, the Universal Thermal Climate Index. So that's not bad. But of course you can't see anything. We could go now here. Gives us data for each hour of the year. Now it gives us a value, which is it's tricky because we can't see it really. It's in a data tree with branches and so on. So what we could do is we could deconstruct the Ladybug data structure. We can get the headers and values in a separate list, and that's how this list looks like. And how that works is that every hour of the year has an index. So the 0 hour is basically the hour from January the 1st at midnight, from midnight to 1 o'clock. The outdoor comfort is the perceived temperature. You feel what the temperature you feel would be this temperature here. So 0.5, -5, -6, -10, -8, -5, and then in the morning it starts to become a bit warmer, it becomes a bit colder in the night again, and so on. And it goes through the whole year, every hour of the day. So this is around summer, where it gets like 26 degrees during the day, and so on. All right, we have this, but we haven't linked it to anything here yet. So we need first the Ladybug human to sky relationship. That again, so this is a new tool we need to add. And now it becomes quite complex already. Again, needs a location. It needs a position and a context. Now the position is as a point. It's a point. So what we would need to do is we need a grid. We need to create a grid on this surface to understand where the test points are. All right, so we have a tool here. It's called Ladybug Generate Grid Point. Oh, point grid, sorry. Here we can place a geometry. Take the surface. Gonna set one surface. Get this one. I would set a grid size, and I'm in meter, and I hope you are as well. So I will set 1 meter here. Or let's make it bigger, 3 meters. I will also limit this already, so at least 1 meter minimum. But you can, as you can already see, we have for every 3 meters we have a grid point, and then we have these buildings. They're probably not really, it doesn't make much sense because they're way too small now for buildings, but it doesn't matter. Tombstones. Anyway, I don't know, it's just some objects. Can they have an influence on my outdoor comfort? So we created this one. Now we have the points. These are the positions I want to test. There could be an offset distance because heat is often perceived more at head height. So I could here place 2 meters. Oh, no, sorry. This is actually, sorry, this is wrong. The height is the height I want to measure it. Let's say 1.6 meters. We are always in meters, by the way. And the context. The context are the buildings. So what this tool does, it tries to understand the relationship between the sky and the person, or the test point. Multiple objects. Is this here? Okay. Also needs a run button, of course. Yeah. Now we get certain things here. Human points. The points used to represent the human subject in the calculation of the fraction of the body exposed to the sun. That's not asked here, but the human line is, I think it's the line of the person. What is asked here though is the fractional body exposure, and we need to be careful here because it might not work directly. So let's see. It's already starting to calculate. It seemed it worked. I'm not sure. Let's see if we have anything. Let's check the values again. Yes, it worked. Okay. And the sky exposure. We also have the sky exposure here. Let's see. Yeah, it's all numbers now. So they fixed the bug. There was a problem with this in the past where you actually had to simplify, I think, one of the two. It already takes quite a while to calculate now. That's a problem because it calculates the whole year. All right. Now I want to do something because the problem now starts already. It's the question, what are we actually testing? But let's go first a bit further. We're gonna end this script so you get a better understanding of what we're talking about. So let's get a heat map. Yes. So we have values and we need a map. Oops, the values. Let's get it. The values here. That's gonna be already not working. I will explain why. So the values are now, the problem now, we don't have just one value for each hour of the year. We have exactly 84 values for each hour of the year because we have 84 points on the grid. For each point now we're calculating the UTCI separately, but then for each hour of the year. So before we divided the headers from the values and we got a list for only 1 point. That was just one list. Now we have 84 lists. So how could we deal with this? Well, we can average this, average the numbers. Now we get another list of numbers. Let's see again how that looks like in the panel. So now we get an average number for each of these points, 84 points. It's now let's just take this and we get it here. We put it here. Now that also doesn't work because we don't have a mesh yet, and probably is also another problem. I will explain in a bit. This tool here is very handy because it not just creates points, it also creates a mesh. So we can use the mesh. Now that's a problem. This is because yes, we have an average number for each point, but each sits in its separate list. So because we created the average for each list. So the lists are still there. There's still lists there. So every point has a list with one value in it. So we can do that by flatten this. We flatten it and here we are. We already have a result. Now I will hide the mesh so we can actually see something. And for these buildings, I will change this to something else. Let me find this. Honeybee is really good with this. I use this tool from Honeybee. It's called Visualize Wireframe. It's quite slow today. With that, I will just visualize my buildings. Oh, no, that doesn't work like that. Must be another wireframe. BREP wireframe. Yes, that's the one. And we also hide this one. Okay. So we can, yeah, it's actually nice to see them. Okay. let's keep it like this. We also want to get rid of these points, and here we have it. Auto comfort over the whole year. It's a bit tricky, really, because we don't see where, I mean, yes, we could say here's hotter, it's more warm, more hot, but actually it's not really hot. It's 6 degrees, but it says something. There could be also that there's a lot of wind and it's actually cooler. How could we move forward? Let's say we capture this the whole year. Now, if we would iterate through that, it would take quite a while. As you have seen, I was just plugging in some of these items like the fractional body exposure and the sky exposure, and it took quite a long to calculate this, because it calculates every hour of the year for each point on the grid. And if I want to have a more finer grid, then it's even longer. The more finer, the more longer. So what I would do first, before we run like a whole year calculation, I would limit the time to a certain time of the year, or like a certain period of time. Now, as you can see here, there is nothing really where we can put a period. Here's legend parameters, legend title, ground reference. There's nothing really where we can do that. So we need to limit the input already. And it's actually a good thing, because it will not iterate through, like calculate everything and then takes a portion of the period. It will be already making the period smaller. We're working with a smaller set of data, which makes the calculation also much faster. So instead of like calculating a whole year, you could also calculate a half year, and that gives you a very good overview over the whole year. All right, so how can we do this? Ladybug Tools. We can go here and say apply analysis period. So we need an analysis period. That's what we need. There's no way around this. Start month 1. Yeah. Wait, let's 12 and 1. We can use that also as end month. We could, for example, just look at 1 month and see how long it takes to calculate. We're gonna use the start day as from 1 to 31. So that gives us 1 month. And the start hour is already given with 0, and end hour is given with 23. I'm not sure actually if there's a day in there. Is there anything in here already? Yeah. It already gives you a period. Now we could also limit that to daytime. But let's work with this. So we don't need to put a start hour, end hour, but we could also limit this for afternoon, for example. Maybe let's do that. From, let's say, okay, this is 23, 0. Let's say from 12 to 6 p.m. Let's put 8 p.m. It's nicer. A lot of people are still out there, or even, especially in Europe. Let's put it to 10. From 12 noon to 10 is my period. You can see it's July, the whole of July, from 12 noon to 10 p.m. So how can we apply that now to the data? We can use this tool here. It's called apply analysis period. And now we need to be careful that we don't miss anything here. Dry pulp temperature, and it's a very good idea to turn this all off, because it would just cause problems. Recalculate. Dry pulp temperature we have here, and we have the period. We have it also here. We use the surface temperature. We use it for the surface temperature. Location stays the same. Don't need to change that. Now I can just copy this. Becomes a bit messy here. I don't like that. It will be more cleaner right away. So what that does is we take the data, whatever data we want to use, and we apply the period onto the data, so we only get a set of that time frame. Now this is the relative humidity, which we need here. We can copy this again. This is the wind speed, wind velocity. Okay, so here we have set it up. Now I can copy this again. Direct normal radiation goes into direct normal radiation here. By the way, there's another way to do this. You can also just plug all of this into one and then select. That's also a way to do it. But I already started like this, so I will just keep it. Diffuse horizontal radiation. Diffuse horizontal radiation. One more. Doing it this way makes sure that you see everything, and then you can always refine your script if you want. But yeah, I think we are good with this. Let me rearrange this a bit. So every data point we change now, we apply the period onto it. So the output needs to be always the same now. If I look into here, it says 330 values, 330 values, 330 values, 330 values, 330 values. Yes, done. Now in here also need to be free. Oh, because this was not running. Okay, I need to run this now. Again, needs to be 330 values. Very important. Here we don't have any data points. This is only the location. It only creates where's the shade, how does the sun relates. Of course, I mean, if there's more context, then that would all go into here, into the BRAP. If there's a city, then you add all this information here, or trees, or any shading. And yeah, okay. Now if I turn this on, if this would turn red now, then you have a problem. Then you probably didn't do this right, but it creates another problem here. Let's see how we can fix that. Oh yeah, we haven't run this. We need to run this as well. Of course. Create a problem. We also need to limit this one here. This also has 8,760 values. That's the problem here. So we could just copy this, and instead of getting data from here, we get this portion, put this in here, and now yeah, works. So you see, I also forget these things, but yeah. So whenever we have data which just goes over the whole year, we need to limit it. It needs to be this. It needs to have the same number of values. Again, here's 330 values. Here it has 330 lists. Sorry, 330 values. Wait, let's check. So here we have 330 values coming in. We have 84 lists with each 330 values. That's what we have. Then we separate the header from the values, and we create the average of that month from 12 noon to the evening, and then we flatten this so we get a number list. And now you can see we get the number list from around 18. It's the average. Now we could of course play with this and say, oh okay, let's check what's the temperature, not the temperature, the perceived temperature, which is the UTCI. What is that in the evening? So we could just slide this here to, let's say, 6 p.m. So from 6 p.m. to 10 in the evening. Okay, that has quite a change. It's quite a change, most likely because of the shadows of the building. Creates it's slightly cooler in the shade. So you have the evening sun coming from that side. By the way, if you want to see that sun path, if you want to see the location of the sun, you could, oh, sorry, this is not the right one. Disconnect location. And instead of using every hour of the year, we could go here with our period. It's the hours of the year. We can place this in here. What else do we need? Center point, sun points. Yeah, it's nicer to look at. Yeah, so we limit, maybe I put something here. Base, I can place some trees, some spheres here. And the radius, let's put 2. So you can see where the sun is coming from. It comes from that side. That's why on this side it's a bit cooler. How could we now how could we test if the position of the buildings has an influence on, or how can we iterate through the building? I mean, the question is about, can we change the building so they optimize the outer comfort? Now we would need to understand what outer comfort means in that sense. So I would go here. If I look at this, I can see 15 to 13 is actually a bit cool. If you had a very hot day, then this is the evening. So let's test during the day, probably better. So let's go back from, let's say 10, takes quite a while, from 10 to 1 in the afternoon. Yeah, okay. So now you can see where the sun would be in relationship. So now we could test. And you, of course, as soon as the script is set up, you could test like a whole year or a half year. But I like to start with a smaller time period. All right, how could we deal with this? So the UTCI, we could say, if I go here, I could read about this. So you can see here, you can see from 9 to 26 is no thermal stress. From 9 degrees to 26. Although I feel like 9 could be already a bit cool. But what's in between? If you would argue that around 21 degree or 20 degree is quite nice. That would be a nice outdoor temperature. So what could we do now here? There are different ways on how to achieve the same result or the same understanding. We could say here comfort, UTCI comfort, or the UTCI. So we have these numbers. If we calculate them all together, so if we create an average of this, we create an average again from these, so that gives us one temperature. Actually, this is really good. It's already at 21 degrees. Let's okay. See, that's where the problem starts. In June in Switzerland, it's actually quite nice. We could, of course, test something different. Seems like Switzerland is a nice country to be in summer. Let's stick with this for a while. It's okay. Let's go for it. We could maybe expand this a bit. So we go from 3 to 3 p.m. Let's say from 12 to 3 p.m. Yeah, it doesn't change much. Let's find a more challenging weather data, because it feels like, and then we can always go back. Probably there could be some fine tuning, but probably doesn't make much difference. Then there are other things more important on how you place the buildings, like program or accessibility and so on. Let's try to find a more challenging weather data. Spain becomes really hot in summer. Let's find something here. Copy Madrid. Here's already a bit different. Not much different. 28. Let's check the wind speed. Be good to see what kind of wind speeds do we have here. Okay, yeah, it's a bit, maybe that's the reason why it doesn't feel so hot. I mean, 20 degrees is quite hot anyway. So that would be outside the comfort zone. Really, it would be outside the comfort zone. Only areas around the building here would be more suitable, I would say. But yeah, we're testing only a few hours. We're only testing here from 12 to 3. This is only 2-3 hours. Nevertheless, we have here 26. It's slightly above that. Now, what we could do, we could argue, okay, this is our massing. We have a certain design we need to follow, but we could shift them around on the site to see if we could optimize. If we could optimize this number towards 21. Now we have 26. Can we optimize it so it moves towards 21? Again, we get all the values, the UTCI values, into here. We split them, the header from the values. We create an average for each point on the grid. That gives us the heat map. And then we create another average of these numbers to get this one goal. This is our final number. So if the average temperature or perceived temperature is 26 degrees, and we try to lower that, can we lower this to 21 by just shifting the buildings? Of course, you can have much more intricate. You can have crazy parameters for your buildings, shape and size and whatever, but that would be probably too much for this video. So I would just move the buildings along a direction and see if that could provide some change overall. So how should we do that? We have our buildings here. Now, instead of keeping them here, we can create, maybe I'm gonna move this here. So I'm gonna take this and place it here. So then one line. Has this changed anything? Not much. But yeah, that would be the first test. So let's do this. We can say move. Again, it's a very simple one. I'm gonna use here human to select the buildings. You can also use your list selection. But yeah, we have these 3 buildings in here. and I'm choosing the first one, and I'm using a Y unit and a slider. Sorry, no, that doesn't work. And what I'm gonna do, I will check. Okay, so here 14 is my maximum, 14, and -4 is my minimum here, -4. Okay, I can basically now shift the building along this x-axis, and I will do this with all of them. Just choosing the second one here, which is interesting, is this one. So now this can also shift. I'm gonna turn it off, and now the last one. It's just to visualize them. Oh yeah, and also want to hide these. Now these are now my buildings here. So the buildings can move along the slider. Gonna flatten this and replace this here. So it's updated to where they are. I'm gonna hide this again. And now I could try to run this. Oh, of course we need Galapagos first. Where is it? Oh yeah, Galapagos. Now, it goes always the other way around. It's I never get it. So fitness. So we're creating a loop basically. The fitness is what we want to move towards. This is the output here. And the genomes are the sliders. These ones. Oops. Of course, again, it's the other way around. I never get it right. But it's the same with you need to hold shift in order to select more of them. But now these can move, and it will always test what is the output here, and does it move towards our goal. And to make this a bit nicer, I'm gonna add here a material so we can actually see the buildings as well a bit nicer. Display, custom preview, geometry. So now actually it's good because we haven't really talked about this yet. There are two different ways to do it. One is a maximum or minimum, or we can set a goal. 21 is our goal. 21 degrees our goal. And we could enable here a runtime limit. By the way, here are links where it exactly explains how this tool works. And then we have solvers. We have two different solvers. Use the simulate annealing solver or the evolutionary solver. I started with I take the other solver because I can see something. And the good thing is there will be an optimum for sure, because you can see already that there are different numbers coming out. But let's see how much that really has an influence. Probably not a lot. So basically what's happening, it will just shift these buildings along the x-axis and calculates the average UTCI and records each result. So then later we can go back to the best option. I will just let it run for now, for a while. It will take a while. I mean, it doesn't do much, of course. So it's also very simple script, but there was some optimization going on, and it's not a lot, 0.1 degree difference, but let's see. So I can go here, and if I double click this, should be, no, reinstate. I need to reinstate, sorry. Now we place the buildings where we had the lowest, or the closest to the goal. Of course, it takes a while because it needs to recalculate it again. Remember this 28.77. Oh, I think it already reinstated it. Okay, so that's already an optimum here. If I, for example, choose the least favorable one here, let's see. So this arrangement had actually less impact than the building being closer together. Interesting. Imagine in countries where it's super hot, actually buildings are always very close together. So that would be now interesting if bigger massing or smaller massing is more successful, and the distribution of that, the size of the road, or the distances between the buildings, if that has an influence. Here it's 28.71, 28.77. So it has, in some areas it has a higher temperature, but overall it's lower. Quite interesting. So this is a very simple example of how you could work on this. I hope you like this video. Now, we haven't talked about the wind, but I feel like it took much longer. That video took much longer than I thought. Of course, I explained the whole outdoor comfort again, but it's important that we go step by step and see all, to explain it really, really well so everybody can follow. So in the next video, hopefully we can look at the wind component. And yeah, looking forward to that. All right, see you in the next video.